Hello, everyone. I can't see myself. Yeah, now I can see myself in the stream. Hello, good afternoon, everyone. Good afternoon, everyone who's here. Devanshi, Shreya, Anushka, Anshida, Shirsha, and all I can see. Let's see the participants. Yeah. Okay. Okay. Welcome mm, to the seventh class. And today we are going to start off with something interesting, something different. So we covered machining and we covered casting, and those were two of the larger chunks of the course. There are other manufacturing processes that we need to discuss, and we'll start off with one type today. Okay, and but before that, I thought, why not, start off with a little video. So I'll reduce the desktop audio on this because I'm not sure. Maybe there are chances that I may get like a copyright strike. Okay, so it's a fairly long, slightly long video, but let's just take a look and let's see let's see the video. Okay, okay. So I found this on Vimeo because, and it's really interesting. Okay, so I'll do some voiceover on top of this. It's really well shot, and I found it very interesting. So I thought, why not show you guys? And in the as the video is going on, why not discuss it with you? Okay. So this guy is making something quite interesting, and I think it will blow your minds by the end of the video. But take a look at how he does it. Okay, that's the important part from the perspective of this course. So you see how what happens when you heat metal? It gets red hot, and at portions where it is really hot, it gets almost white. So he's working with steel mostly. Can you hear me? Is the sound and all good? Just tell me, give me a heads up. So look at the amount of effort that is being put in, right? You know what I'll do in one of the exams. So we'll do a test sometime in the next module, and I would expect you to go through some of these videos that I'm showing. Okay, because I might ask you some simple questions from there. So he's trying to make a spring, huh? He's bent a piece of sheet metal, wrapped it in wire, coated it with a kind of chemical. I think it's borax. It's a kind of flux which prevents the metal from oxidizing too much. Okay. Yeah, totally. Madhav, editing is amazing. I mean, it's edited to the music. Okay, you saw he dipped it in oil after he did that, and now he's taking it into the various machines and machining out some interesting shapes and all that. Okay, the guy is so good that he's making his own screws and all. Okay, and this process, can you tell me what this process is? Anirudh, we have a furnace. We do have a furnace, but it's not like very high temperature. I think it goes to around 800 degrees or so. Okay. Look at the details that he's getting out of these machines, and hammered forged parts. So what the initial steps were forging. Okay. Yeah, Gaurav, you're right. It's called tapping. Okay. And once all of this is assembled, it just looks phenomenal. That is one. But you see how it works. Okay. That's the best part of it. Okay. This is what he made. Just look at the keys that are there. I don't think anybody will be able to open it up just like that. Amazing, right? I think it's called it's by Seth Good, and filmed by this guy, and it's a really well edited video. I hope somebody does not take it down. We'll see what happens if that is done then. Okay, so we will not play the next video naturally, and let's go back to our classes, right? So you saw what happened in the video. It's almost like he went through almost all of the machining processes that we discussed, except for casting. I don't think there was casting, but there were bits and pieces of a lot of these things. So if you analyze the video, you will find some interesting things to take away, right? So I would urge you to go back and look at the video again and look at it piece by piece, and see what you can find from there, what kind of details you can see from there. Okay, so let's jump into our presentation, and let's see what we have today. So it's not day 6. So this is the link of the video. It's there in the presentation if you want it, or you would want to see it later on. So this is the link of the video. Okay, and so today we are moving from the liquid part, the side which is you see on top here, right? So from that part to this part here. No, wait, that part. No, wait. That one. We are going to the plastic phase. Okay, so we are taking a look at how metal is manipulated when it is in a softer state. It's not in a molten state altogether, but when it is softer. And how does metal get softer? You heat it, and it starts melting, and naturally the way it solidifies, the similar way it melts, it starts melting at the grain boundaries, and there is some scope for the crystals structure and the grain structure in the material to rearrange itself when it is being worked on. When I say worked on, that means when it is forged, when force is applied to it. Okay, so we'll start taking a look at these processes. So the third diagram over here, so right, the third diagram that you see, so these two are the phases in which we will see how metal is manipulated. Okay, so the topic that we are discussing, it's called metal forming, and in the way you manipulate liquid material, mostly liquid metal, is through casting processes, and the way you manipulate metal when it is in a plastic state is in forging, called forging. And you could use similar forging methods when the metal is at room temperature also, when it is not heated. So there are some processes, some forging processes, or should I say forming processes, which are done when the metal is solid. So we will take a look at some of these also, but we are the fundamental, the theory of manipulating metal when it is not in liquid state, so those are fairly similar. Okay, so we'll start off by first looking at forging. Okay, yeah, we discussed this chart. I don't know, I think by mistake I put this over here. So this is how solidification of metal happens. I discussed this earlier, and I discussed how when, let's say, you have a cube of liquid material, when it cools down, what happens to the grain structures depending on the rate at which it is cooling. So if the rate of cooling is quite high, then that means it is losing a lot of temperature very quickly. Then chances are you will have this kind of a grain structure where you will have a thin boundary around the object with smaller grains, because a larger amount of heat was released from that area very quickly, and the crystals did not get a chance to grow as much. However, as you go in, you will have these dendritic structures, you will have these kind of columnar structures of grains which will be towards the center, pointing towards the center. If the rate of cooling is much slower, then what you would have is, towards the center you will have this kind of a zone where the rate of cooling is very very slow, and the grains get a lot of time to grow and rearrange themselves and remove any internal stresses because of the varied orientations they are in. And this is the equiaxed zone, and it is possible to get a completely equiaxed structure. An equiaxed structure is something that will have more uniform and non-anisotropic kind of material properties. So it is more desirable to have in a homogeneous grain structure, but it's not always practical. However, it is possible to do it by using some additives and all these kind of processes, right? Okay, so we'll take a look at plastic state forming. These are some of the processes that are there. Let me move myself to the other side. Where is my mouse? Right. So these are some of the processes that are there in plastic state forming when you are trying to form metal. Okay, so first one is called forging. Forging and forming are two different things, right? So forming is like the whole umbrella term. So you form material, you give it, you take the material and give it some form. Okay, by applying force and pressure and whatever to it. Forging is a subtype of forming where you heat the material to a certain temperature where it is more malleable than, let's say, when it is solid, and you apply force through various processes. You could just hammer it, what you saw in the video, that was hammer forging. You could do it at a larger scale. Of course, you need a much larger hammer, and you can have something like drop forging, where instead of multiple hits of a hammer, you have one very large, very heavy piece of material or die just falling into the heated material and giving it a certain shape. So that is drop forming. Press forming is, instead of dropping something on top of this heated material, you press it slowly so that it could take the shape. And swaging is a subtype of forging which is specifically related to pipes. So let's say you want to join two pipes end to end, right? So one way to do it is to weld it, but how would you do it with forming? So you would need to increase the diameter of one of these pipes to a larger diameter, push this other normal diameter pipe into it, and make sure that it is clamped. So this process of increasing the diameter of a certain section, that's called swaging. Okay, and this is also part of forging process. Then we have a subtype called rolling processes, rolling forming processes. And rolling is basically used for making pipes. And it's a separate category of manufacturing processes altogether, because pipes are something that is absolutely essential in modern manufacturing and plant production environments, right? So everything from starting from critical gases, LPG, and all these things are transported through pipes, and they need to have certain strength properties for it to work properly, right? So rolling processes is used to help make these kind of, or no, I'm sorry, I made a mistake here. Rolling is not that, right? So rolling is basically forming the material. There's no way to edit it on live, so my mistake will always remain there on the internet. So rolling is basically giving a material some shape. So let's say you have a thicker material, you have rollers that press the material to a certain thinner shape, and you can do it when the material is hot or when the material is cold, and that is cold rolling and hot rolling. Okay, and rolling is a specific process that imparts properties, some significantly different properties to the base material. So let's say you when you go to the market, no, you can buy rolls of steel. Okay, and these rolls of steel come in variations like hot rolled steel or cold rolled steel. Cold rolled steel are much harder, and they have a surface which is very hard, and they are difficult to cut. And generally these almiras, Godrej almiras that you get, metal almiras, they are made with cold rolled steel. Okay, similarly you get something called hot rolled steel, which has its own set of applications. Okay, so rolling is that, not pipe forming. Sorry, I made a mistake. And then we have this type of process called drawing process. And don't understand drawing like you know like drawing. Okay, just give me a second, I have something. Okay, yeah, so drawing process is basically to draw. Okay, to draw means to pull something out of something, right? So a drawer is, let's say this, I have a drawer, so that's why it's called a drawer, because I can draw it away from the table, right? So you can't see it, but yeah, it's there. Okay, so drawing is have you ever seen your grandmother or mothers making these thin um, uh, you know strands, suta, from a ball of cotton for use in a diya? Let's say if you are if your household follows Hindu customs, then you'd have this puja sthal where you'll have a diya. And traditionally, a lot of grandmothers used to make this small bati from these balls of cotton. And have you noticed how they make these batis, right? So they would pull a small strand from the cotton piece, and they'll rotate it, and they'll pull the whole thing, and a string would come out, right? So this is the process of drawing. Okay, so in this forming process, you would try to pull the material from a certain base shape. Okay, and there are various types of drawing processes. There is wire drawing, which is something similar. Okay, there is tube drawing, where you would where the end product is a tube, and similarly a bar. Okay, so this is a drawing process. And then there is something called an extrusion process, and this is again going back to our households. If any of your mothers, if you've seen them, or if any of your family members, if you've seen them making bhujia at home, you would have this small container filled with batter, and there'll be small different shapes that you can put in towards the end, star shape or something circular shape, and you'd press it, and the material would come out, right? So and then that would be fried, right? So that is extrusion. So drawing is slightly different than extrusion, Fayaz. So drawing is the thing that you are you want as the final output, that is pulled from a material. Extrusion is where what you want is pushed from the material. So there's a slight variation, and when you see the actually schematics of how these things are done, then you'll get a bit more clearer understanding. So this slide was just to give you like a larger snapshot view of what exactly entails in these forming process, and all of these processes are done primarily considering the fact that metal is soft, is behaves like dough. Okay. Devanshi's question is, how does cold rolling come under plastic forming? Well, see, okay, here's how I will answer this. So, metal is not a solid thing. Okay, so metal is actually soft. It depends on the force that you add. If you can apply very little force, then the material is hard. Okay, is not very strong. But let's say you have the ability to apply how much ever force you want, right? So let's say you are Superman, okay, or Superwoman, and if you have infinite amount of strength in your hand, if you press a solid piece of steel, right? So let's say something like this is a solid piece of metal. If you press it, no, it will behave like a soft material. Okay, I'm sorry about that. Let me just, yeah, okay, so it will behave like a soft material. So in cold rolling, the forces that you apply are much higher than hot rolling, but the process is exactly similar to a forming process. It is taking advantage of the fact that metal is actually a soft thing. Okay, so I hope I've explained it in a manner that you would understand in a very basic sense, right? So that is why it's there within this forming category, where you are actually forming the material. Okay, so let's go forward and let's see what we have. So this slide kind of gives you the answer, why do we need forming at all? I mean, what's the point of forming? Yeah, I understand, but you could do a lot of things. So let's say the person that you saw, he hammered things and he got these things into shape that he wanted, right? What's the point in that? He could have just cut a piece into that shape. Okay, there will be some wastage that's there, but yeah, I mean, why go through so much effort? Okay, and you would understand why we need forming if you look at the microstructure or the grain structure of the formed material, of the formed piece. Okay, so let's just take a look at this. So this image shows you three metal objects which are made from, let's say, a similar material but through different processes. Okay, so first one is casting, and I don't know if it's very clear to you. Why do you have so much respect? I mean, right. Anyway, sorry. Don't distract me. Yeah? Anyway, so casting, right? So let's say if you have casting, what would happen if you look at the grain structures inside a microscope is you would see these grains which are arranged, like mostly uniformly, or let's say towards the outer envelope you would have smaller grain structures, and towards the inner, like you said, like we saw it, there may be like a equiax structure. Okay, so you would have this kind of a grain orientation. There's no particular direction to the orientation of the grain. Okay, they are just haphazardly arranged, more or less. Now if we take like a solid piece of material, okay, and if you cut a similar thing from this from such a stalk, okay, if you cut it from a stalk, what would happen is that the grain orientations would follow the shape of the initial stalk. So let's say this was cut from an initial stalk which had grains aligned like this, right? So like straight, like you see in this lines, right? Like these lines. Okay, so when you cut, you would have these locations where it's not flowing along the shape of the object. Whereas when you forge it, it's you can ensure that the grains are actually following along the surface. So naturally, you get an impression that maybe this is better, maybe in terms of strength, than all these two. uh, why is it better, we will discuss slightly later. So these same kind of details are seen in other forged parts also. So these are also other examples. So a lot of times what you do is gears which under which probably will undergo a lot of stresses, instead of making them through traditional milling or machining processes, or let's say casting them and milling them, you can make them through forging. And what that does is it orients the grains in such a manner that the surfaces of these small gears become extremely hard and extremely strong. And if the surface is strong, then chances are that it can withstand a lot of force. Okay, so yeah, so that is the main reason. Same example over here, if we have three parts, if we casted, this would be the grain orientation. It will fairly haphazard. If you cut it from a stock part, you would have this kind of an arrangement. And if you cut it, if you forge it, then you can ensure that the grains are flowing properly. Why do we want grains flowing properly? Now think about this. So let's say this is a gear tooth, okay, and when a gear is moving, there's a lot of force and stresses that comes onto the gear, um, tangentially to the axis, or tangentially to the circumference of the gear. So let's put it that way. So imagine this is a gear, this is a tooth of a gear which is very very large, right? So there'll be forces which kind of press on this surface, okay. And what will happen if the grains are arranged in this manner? There are chances that if there is some kind of high shear forces, then these would break. There would be fracture that can easily propagate through these grain boundaries, between these grain boundaries. So think about that. So grains are just like they are arranged like this, like this, like this. And if there's a crack, then there are chances that it is more easy for the crack to propagate through between the grains, rather than splitting the grain into two pieces. So yeah, so that way this kind of allows some scope for such a thing to happen. Okay, whereas if you look at this, if a crack starts here, then it is quite difficult for it to propagate slowly, right? You can think of this thing like, imagine this is made with a stack of you know let's say plastic or cardboard, and if you press it, press the stack from one side, then it will kind of slide off, right? So if this is the stack, then it will kind of slide off. Whereas if you formed the cardboard and stacked it in this manner over here, then if you apply a lot of force, then it will deform rather than sliding off. So these kind of things are there which benefit the, or makes a forged part much more stronger. Okay, I hope I'm making sense over here. Now uh, again, another kind of macroscopic view. So let's say we got this kind of a piece, this ingot is like a it's a term which is, it's a jargon which is typically used to denote these pieces of material which just have come out of casting. Okay, so they are casted in pieces, in standardized ingot pieces, right? So these are ingots. So ingots, let's say you take a section, and this is probably how you will see the grain structures internally. You'll have a layer which has cooled faster, so smaller grains, and you will have these dendritic and columnar structures, and it's naturally not uniform. And think about that, if there's some kind of shear stresses that come into this part, then chances are the cracks will propagate easier through the central places where the grains are meeting. Okay, and So this is how typical ingots are there. And what happens in manufacturing is that you don't directly use these ingots to start off with the machining and manufacturing whatever things you want. You would take them through these forging processes, which uh, you know regularizes or homogenizes the grain structures. So after a little bit of beating, hammering, heat treatment, and these kind of processes, you can ensure that overall internally the grain structures are arranged more uniformly than before. Now to get like so I took this ingot and I did some heat treatment to get these kind of, let's say, uniform grain structures. So after this I realized that the strength that this thing is showing me, or the hardness, the surface hardness that this thing has, is not adequate for my requirements. I need something a little harder. And how do you make the same material with the same composition slightly harder than before? If you can have a layer, or the whole thing can have much smaller grain structures than what is, let's say, currently it has, then I can say that it will become more harder. So this process is a process of rolling, and this image shows you what happens when you roll. So imagine there are two. Let me get back my and how where are you? Yeah. Right. Okay, so imagine there are two rollers here, right? And I am pushing these two rollers against this piece. Okay, I'm pushing these two, and this thing is being rolled like this, and this thing is being rolled like this. So this material is being pressed or pulled towards one side. Okay, so what happens to these grain structures when it is being rolled? Okay, naturally, because of the force, they kind of elongate into these shapes, right? So like this. So these are the deformed grains that were earlier there. So internally the crystal structure kind of breaks down and rearranges itself into newer crystals, and newer boundaries are formed. But sometimes there are some places where it's not really able to form a uniform grain. Internally there are a lot of stresses within the grains. Okay, so now what happens is that uh, as this kind of goes on, right, as this goes forward, as it cools down, no, these internal stresses inside the grain, okay, they become too much for that grain to bear, and newer boundaries are formed. Okay, so this material is very hot, by the way, and it comes out, and as it cools down, something called recrystallization happens. Okay, so recrystallization is just what it sounds like. New crystals arrangements are formed. Okay, and it starts forming, let's say, from here to here. Okay, and here it has recrystallized. So as you can see, this process of rolling, with this process of rolling, we are able to convert the sizes of grain structures from, let's say, larger structures to smaller structures. From here to here, going from here to here, you would need something like heat treatment. And if you have read the part in the Kalpakjan book which I told you to, if you've read that, then you understand a little bit what heat treatment is, right? Anyway, okay, so this is how rolling kind of benefits the, or improves the strength and the hardness and all of these kind of mechanical properties of the material. Okay, and this two images shows you two different versions of rolling. One is a hot rolling, one is a cold rolling. So what happens naturally in hot rolling is that because the material is hot, the grains have slightly more, they have a ability to give way, or they have ability to break apart more easily. Okay, so this one is a heated material. It goes through the same kind of roller setup, and what happens is, if newer grains are formed towards matlab, as in like throughout the, they can be found throughout the cross section of the material. Okay, in cold rolling on the other hand, what happens is that because the material is cold, it's not heated to a certain temperature, the central portion of this doesn't get the grains in the central portion of this doesn't get modified because of the applied force. Most of the deformation, right, it is absorbed by the grains that are there at the surfaces of the material. Okay, as you can see here by the orange diagram. This one is taken from, I think, Jim Lesko's book. I think so. Okay, I may be mistaken. Okay, anyway, so yeah, so the difference between these two is should be fairly apparent. So first one, the cross section, across the cross section, the strength and the mechanical properties of the material are fairly uniform. Okay, so you would have the same kind of hardness towards the surface as you would have, let's say, towards the center. Okay, it would have a more it would be slightly more bendy. It would have slightly lesser stiffness as compared to this, because in this one, you should try this. You have two stronger materials and you have a structure in between. No, this behaves much stiffer than, let's say, this kind of an arrangement. Okay. Right, so this is the difference between hot rolling and cold rolling. Okay, so the grain transformation that happens in cold rolling is limited to the surface, which makes it much harder and much stronger than typical materials, right? Naturally, hot rolling is slightly more costlier than cold rolling, because you don't have a parameter of temperature to control that much, right? And most of these sheet metal objects that are made with cold rolled steel, and it is slightly cheaper in cost, and it is widely available, and it is versatile. When you cut it, you just have to ensure that you have enough strength in the cutting apparatus that will go through the top surfaces very easily, because the central surfaces are more, or central portion of the object is more easy to cut. Okay, so that way manipulating it is a little easier. And yeah, so and also I think because of the nature of the grain arrangement, the forming, giving it a certain shape, right, that is also much easier, okay, then let's say something like this. But this one also has its own set of advantages and applications. Okay, I think it's the same idea, and we'll skip and we'll move forward. So that rolling setup that you see is actually not done by a single two set of rollers, because the amount of force required for something like this to happen is immense, right? So you actually have this kind of an arrangement where the force is finally transferred by just two of these rollers, but the whole arrangement has multiple rollers like this, which kind of amplify the load that comes into these final things, right? So this is how the actual setup is, right? So you have secondary rollers, and you have some kind of so these are the driving rollers which run the whole thing. These are not, the motor is directly not connected to this, but rather these ones. Okay, and these ones apply the force. Okay, so this is how that setup is. And rolling is something that's like absolutely essential if you look at the construction industry and the large scale for example, the railway industry. Everything in all the railway tracks are made using rolling. Okay, so and this is an example. So here what they are making is, what they are trying to roll something called I-beams. Okay, I-beams are used in constructing very large skyscrapers and all of that. So they are the internal foundational elements. Okay, so you'd start off with a simple billet is basically a rectangular cross section of material, and you would pass it through different sets of rollers, and subsequently in stages you get to like this eye shape, which has a lot of properties which are desirable for construction. Like for example, it has good resistance to bending moments, and it the strength the that it has across, you know, the because of the shape, the strength of that small piece of material, which does not take too much material, is very high than, let's say, even a, you know, solid piece. Okay, and rather you, so it's a good trade off between lowering the amount of material that is there and the strength that is required. So that's why I beams are really really, you know, essential for construction. Okay, so this shows you how I beams are made. So you take a billet, you run through this kind of a first stage roller where this shape is achieved, then it's pressed, then you have these side rollers which kind of pinch in the material in subsequent stages. You get something like this, and finally flat set of rollers gives it this eye kind of shape. Okay, I think I should have like a photograph of an I beam on the side, maybe in the next year thing. Okay, what are the advantages of uniform grain structure? uh, there, I mean, in comparison to, let's say, a non-uniform grain structure, in between, let's say, comparing cold rolled and hot rolled steel, uh, a uniform grain structure ensures that there are all the material properties are non-anisotropic. I mean, like the strength, the the ability to the strength of the material, right, it does not vary across cross sections. Okay, so that is the advantage of a hot rolled kind of material. Whereas cold rolled, let's say, for me it's not important to have like non-anisotropic properties, right? I can have some variations in the, let's say, lateral sections, but in the axial direction, okay, I need really really good strength. Okay, or maybe it's the other way around. In the cross section side, I need uniform strength in some manners, and actually if it's slightly here and there, it's okay. So it's a kind of a trade-off, and naturally, if you look, the uniform grain structures would definitely have a slightly better, property. But if you have like a non-uniform grain structure where you have larger grains at the center but thinner smaller grains at the surface, the surfaces become very very hard, and that is a very desirable property, especially, let's say, if you're making an almirah. You don't want dents and dings happening all the time and scratches happening very easily. So these kind of things make it like a trade-off. It's just a trade-off, right? So one thing is slightly more costly, the other thing is slightly less costly or less costly, but the strength is variation is slightly different. So you choose which one is more suitable for you. Right. So I think Devanshi is saying train bogie floors are made with I-beams. I think so. I can't tell you correctly, but yeah, maybe. Okay. So the next one is, how do you make pipe? You can make pipe using forging methods. Okay. So this is an example. So if you take like, so you can do this actually. If you take like a piece of dough, play dough, right? If you take a cylinder of dough, play dough, which is solid, right? And if you roll it between two surfaces, no, you will see what happens is internally, no, there'll be a slight cavity which is starting to form. Okay, so let me just draw it again on this. And so what happens if you, so if I take a cylindrical Play-Doh piece, and if I, let's say, roll it between two surfaces. So this is one surface, and Anyway, so what happens is, if you move this forward and back, right? So what happens is, you get, after some time, no, on this surface, no, what happens is, instead of this kind of a straight cross section, my this thing is becoming very jittery. Anyway, so you'll get this kind of a arrangement. Okay, I'll just sketch over here. So you'll get this kind of a cavity which is forming, and slowly on this side, no, you'll get this. If I draw again, so you'll get this kind of a thing forming. Okay, so this starts forming, and this is what is being shown here. So you take two plates and you move it slightly and this way, and you press it, no, slowly a small cavity starts forming, and in that you can put a rod, you can put a mandrel. Okay, this is called a mandrel, and you can push it and it starts becoming like a pipe. Okay, so it's possible to make it into a pipe. It's possible to form or forge a pipe, or form a pipe, right? So, but this is not very clear. This diagram, I mean, I don't think it does justice to the intricacies of the process and how elaborate this whole process is. So there's this very interesting video. I have reduced the volume of it because it's just like ambient noises mostly. I don't know if you can hear it, but this is an animation. So it starts off. Let me just give me a second, right? I hope you can hear me still. Yeah, can you hear me? Just tell me if you can hear me. Okay, so right, so let's start off from here. So this animation shows you the whole process of forming. So you have a solid piece of steel, let's say, okay, and this is all mechanized, and there's a very large furnace called a rotary hearth furnace. Okay, and a material is put in from one end and it goes around, and by the time it comes to the other side, no, to the same place, it's white hot. Okay, so this is the rotary hearth furnace. It's very hot, and from one end to the other end the material is heated and it comes to the end. Okay, and this is transferred through these kind of arrangements to a place where there are rollers which press the material. Okay, so this is what the diagram was trying to show. It presses the material, and what you have is this kind of a separate piece which is called a mandrel, which pierces the material, and it goes through subsequent rollers, and the mandrel is inside the pipe itself. Okay, along with the pipe you have the mandrel also. Now the mandrel is removed by a next set of rollers, and you have these kind of arrangements where it is quenched, or rather liquid or water vapor is poured into the material to reduce its temperature, to control its temperature, and slowly through these rollers it comes out, it gets pressed, and the mandrel is removed from the other end. Now the pipe essentially is ready, and you have these kind of rollers in subsequent phases and in a certain arrangement, which take down the diameter of the pipe in stages. So this you can see, I think it's a very nicely done animation, and it shows you the details, right? So now it's just a matter of elongating the pipe to how much ever diameter you want or length you want, right? And this one is a quenching setup, spray quench. So water is poured onto the surface of this to harden it. So this makes it really hard, but it also makes it very brittle. Okay, this quickly cools down the material. So you can imagine whatever shape in which the grains were in the center in the object. Yeah. So I just went off. The video finished just like that. Okay. So I hope you understood how it happens. So this is the quenching again. So you can imagine what happens when you quench something. Whatever grain orientation or structure currently they are in, this kind of get locks that into place. Okay. So they don't get too much time to grow or anything, right? So that way the uh, you know yeah, well, so this makes the material very very brittle. Okay. The quenching part of it. Okay, let's go forward and let's see what we have here. And this one I think is the same thing but like the real world. Okay. So this is how the industry, rolling industry works. And this, you see huge machines just making pipes. The whole industry just makes pipes. So you have these billets, and this is the rotary hearth furnace. Oh wait, just wait, let me. Okay. So these are the billets that are there, and Chaitanya is asking what difference do we see when we put hot steel in oil and in water. It's not much difference. Both of the processes are quenching processes. Oil, the reason you use oil is because it doesn't release so much fumes or vapor, and it has a larger, what's it called, it can absorb a larger amount of heat before boiling off. So whereas water, I mean, as soon as it hits 100 degrees it boils off. And there's also this whole thing called the Linden frost effect. Okay. Which is basically water vapor kind of forms like an insulating layer, which prevents the liquid phase water touching the hot surface. Okay. So which reduces the performance of quenching. Yeah. So those kind of things. Yeah. I mean, this is Aditya. This is the right time for all the yeah. What's that? What's the last airbender memes and all that? Anyway. Yeah, so this is the same thing, but shown you actually what happens in the actual setup. Anyway, we'll not take a look at this. Let's move forward. There is other ways of making pipes also, and this is one of the ways which uses liquid material. This is a casting process and not a forging process, but just for you to have an understanding how would you make seamless pipes, right? So this is a process where liquid material is poured onto a rotating substrate. Okay. And as it rotates, liquid material is poured, and that kind of deposits and cools down on top of the substrate, and you remove the substrate when after it's done, and you have this kind of a pipe. Okay. Manu is asking why is that why water is sprayed rather than just dumping onto water? Is that why water is sprayed than just dumping into water? I'm not sure. I'm not sure if Lindenfrost effect explains that thing. I'm not sure. Okay. Maybe. Okay. Okay. Anyway, so let's move on to other kinds of forging process. So that was rolling. Rolling kind of gave you an idea about the internal structure. So that kind of explains you why forging is important, right? The process of forging changes the grain structure in a manner which is beneficial to us. It increases the strength properties and all of that of the same kind of piece, right? So that explains that. So let's take a look at the manufacturing processes themselves, and as you can see, the scale at which forging can be done, right? So this here that you see, that is the person, right? So this guy is handling this, right? So and this is huge, and this is probably like you see these people, like this is probably a blank, or the starting point of making a gear for a ship, okay, a large ship engine, okay, so or like a crankshaft or something like that. So you could machine, so once this is forged, you could machine just portions of it off, and the main thing is forged and you get the strength, right? So yeah, so let's take a look at forging. What are the different processes? This is just like a simple die forging, what happens and how the material changes when you press it. So you have this workpiece which is heated to a red hot temperature. You press it with the die, okay, in this case it's a flat die, right? And you have this kind of a barreling effect. What happens is, at the places where the die touches the material, there's a lot of friction which prevents the material from spreading out, and it spreads out rather in these other places where it's not touching, right? So you get this kind of a flattening effect. It's fairly intuitive if you think about it. So this slide shows you something called die forging, where you have the you have a top die and a bottom die. The bottom die is held securely, and the top die, let's say it moves, and you have the blank, which is maybe a square or a cylindrical piece, heated to a red hot temperature. I think the red hot temperatures, when I say, it's something around above 1100 degrees or something like that, okay? So you heat it to that temperature, and then you press the whole thing with a certain amount of force, and it takes the shape of the die cavity, okay? So there are some like thumb rules that are very very essential when you, let's say, think about designing for forging. First is, naturally this is like a very crude method, you can't get very fine details with it, okay? So you should always have a large filleting and radii that you've put in for the forged part, and there is some tolerances that should be considered. Like for example, when you press, there's some, so some amount of wear happens of the die. The die is not something that is always there, so some amount of the subsequent pressing and all, you can imagine this is red hot steel, and that is some, let's say, tool steel, and if you keep on pressing, some amount of, because of the forces, some amount of wear and tear happens to the die. So you need to consider all of that, okay? And I don't know why I have put all of this here, but yeah, I think what I want to say is, these kind of materials, everything can be forged, yeah, maybe, but yeah, I think some misplaced. So how would you go about using this process, okay? So I want to make a gear. I want to make a gear which is shaped something like this, and this is a shaft which will fit into whatever place is required, and this needs to have some kind of arrangement, some kind of toothed arrangement which kind of locks into that place, okay? So let's say a star shape or something like that, and these are the actual tooths of the gear. So you could directly, you could try to forge this, but it's not possible to get these kind of details in forge. So you do it in steps, okay? So in the first step, you cast something like this, and it's called a blocker, okay? A forging process starts with something called a blocker, and that is taken through to a first pass of forging. So first step is forged, okay, and that is more or less finished, and then after that you take it either through machining or through subsequent stages of forging to come to something called a near net shape, okay? And then after that you machine whatever is necessary, and now once this is done, you can imagine some portion of it, of the top surface, may be machined off, so you need to heat treat it to get it to the right kind of mechanical properties that you want. Okay, so let's take another example. This is a connecting rod in an engine, in an IC engine. So this one, I think it connects the crankshaft to the pistons. Okay, I think so. So this is the shape of that object, and the way so naturally you can imagine a crankshaft is something that undergoes a lot of stresses, and it has a lot of cyclic loading, right? So the forces that come into play are in a cyclic format, and it needs a lot of fatigue strength, right? Endurance, right? So forging ensures that you get a part which is strong in considering the fatigue strength. Okay, and the way you get this kind of a connecting rod, the shape you'd make something like this is you'd start off with a cylindrical rod, which is a blank, which is called a blank, and then you first do the operation where you get the edges of the object into a shape that after you press, the details are achieved, and whatever is necessary, whatever is not necessary, whatever material is not necessary, it flows out from the places where the two dies are meeting. Okay, so here this is an edging operation, shape is got, and the next forging operation gets these kind of details where you get the block, and in the next set of operations this is refined even further, and after that these outer parts, which are called flashes, are removed off. Okay, so this is a step by step process, and yeah, I mean, like, this kind of gives you the same idea. Okay, so so naturally here, if you have noticed, then it's very difficult to get undercuts. Here the dies, if the object is not designed in a manner that it can easily be encased in a die with a top cavity and a bottom cavity, it becomes difficult. However, so for example, if this piece has had a small hole on this square kind of a place, right, then it would be slightly difficult to do it. That would be an undercut. But that does not mean it's not possible to get undercuts. You have specialized forging processes which can be used for forging complex shapes. Here, for example, this part you want forged. Okay, so you have a top die and a bottom die that gives you the near net shape, and then there are two plugs from the side which also are forced and into the material to get these undercut sections. Okay, so however, naturally this is extremely expensive, and it's better to concentrate on, simpler forging applications of forging. Okay, right, right. So let's move on. So this is one of the most iconic designs of scissors. Okay, it's done by Fiskars. I think it's a very old design, and now it seems like, अरे ये क्या है, तो बहुत ही simple है. I mean, you would say something like कि I've seen this n number of times in tailor shops and all that. Actually, this design is like, it's so good that it's kind of flown over or spilled over to these local manufacturers and all that. So this is like a really iconic design, and this one is by Fiskars, and let's take a look at how this would be made, right? So let's take a look at that. Okay, so this is from that oh yeah, how it's made series. So let's for this one I want to just crank up the volume just a little bit so that you can hear, and we'll pause in the middle and we will discuss what we are seeing. Okay, just give me an indication if
when you're talking about
sound
metal.
is okay.
Many industrial machines contain steel parts that have to withstand great stress.
Right.
The metalworking method that produces the strongest steel parts is forging. heating the metal, then
So
forming
let
it to
me
the
just
required size and shape.
give me a second. Give me a second. Yeah.
Steel forgings are made from scrap iron.
So
Pieces of used iron recovered from demolished buildings and old cars.
so this one gives you an example where scrap iron is recycled into making these forging parts. Okay, and
As well,
this is a large magnet. I think he already said okay, it's lifted up by large magnets. Anyway, so it's a large electromagnet which pulls up metal
as bits
and
of new iron left over from the manufacture of iron products.
okay. And typically, this is done in recycling industries where you would take some parts of recycled material and some parts of, these, uh, I should say, virgin material, and that you mix it together and kind of get these. Sorry, sorry.
Forgings are made from scrap iron.
Yeah.
Pieces of used iron recovered from demolished buildings and old cars, as well as bits of new iron left over from the manufacture of iron products. Forge workers maneuver a gigantic magnet to lift almost 6 tons
Now
of
he
scrap
says,
at a time,
yeah.
until they filled a 28-ton scrap bucket.
So this one is melted.
Use 2 such loads into a fiery furnace whose temperature peaks at 3,000 degrees Fahrenheit.
So this one probably is a steel furnace. That's why the 3000 degree Fahrenheit. I think it's around 900, 1900 or 2000 degrees centigrade, something like that. Or is it around 1700? Yeah. Anyway, I can't convert just like that.
This is called an electric arc furnace because the heat is created by a strong electric current running in an arc between 3 electrodes.
Anyway, so all of this scrap is dumped into that.
Subgrades of steel. They're produced by adding specific metals or non-metallic chemical elements such as aluminum, nickel, chromium, vanadium, manganese, carbon, and molybdenum.
Right. So you saw these. So what they do is typically when you get this kind of iron, you melt it, and when it is in the furnace, when you add, that's when you kind of measure and add these different elements into the mix. Okay, and that everything melts together and boils together. It's almost like cooking. Okay, it boils together, and when it cools down, the alloying of the whole thing happens. Okay, so this is how alloys are created. It's like a very simple straightforward process, right? It looks okay, it's obviously not. There's a lot of control and process parameters that you need to monitor, but yeah.
They also add the mineral fluorite to help fuse the metals,
Okay.
some of which are in the form of blocks called ingots. Throughout the 3.5-hour meltdown, they test and adjust the chemical composition.
So this is how it's done.
Try to attain the lowest hydrogen, oxygen, nitrogen, and sulfur levels.
So the reason he's saying that all these nitrogen, sulfur, all of this is reduced is because they kind of, these elements typically are the impurities when you consider molten material, and that either that can get into the product itself and make it undesirable, or it can form this kind of layer on top which is called slag. Okay.
Key to producing strong, high-quality steel. Then they pour the sizzling molten metal into a 50-ton ladle that's lined with heat-resistant brick.
So what he said, this is poured into a ladle which is lined with heat-resistant brick. Heat-resistant brick are these refractory materials, so things like ceramic or in the category of ceramic. Okay, so this one is lined with those materials so that it does not it can hold the metal, right?
They add aluminum and lime to chemically counteract oxidation,
Right.
rusting caused by air exposure. Now they cast an ingot, a block of steel that they'll shape into a forging.
Okay, so this is from here. Sorry. So from here it's
Now they cast an ingot.
till here it's casting, right? But you are not casting the product. You are casting uh, a piece from where you would start forming and forging the part.
A block of steel
Okay.
that they'll shape into a forging. The molten metal flows out the bottom of the ladle into a mold below. This bottom pouring, as it's called, makes for a smoother casting because liquid flowing downward doesn't swirl around as much as liquid poured sideways. This forge can cast ingots weighing up to 46 tons.
Okay, so just look at this size of these things. It's
The ingot solidifies, and they turn the mold upside down to extract it. Then, over 12 hours, they
I just want to do like a side note, and I want you to appreciate the design of this jaw. Okay, it is so simple, but look at it, it's so effective. The force of holding this object, it's coming from just the lifting force. So you have this one lifting point, and these are two arms. There's three pivots: pivot 1, pivot 2, and pivot 3. And when you lift it from here, these kind of pull from both the sides and it presses on this side. So all you need to do is you need to drop the jaw into the object in an open open configuration, and when you pull it, it automatically clamps onto the object and lifts it up. So yeah, well, side note. Okay,
hours, they reheat the ingot to 2200 degrees Fahrenheit. This makes it soft enough to hammer or press into shape.
so now it will be pressed, and I want you to notice
They
something.
use a machine called a forging press, mounted inside a forming die or a pair
Okay.
of dies, depending on the technique they're
Notice, okay, just notice. Wait, I don't know if you'll
The
see
press
here.
applies thousands of tons of pressure,
There.
crushing
Okay.
the ingot and forcing it against the die.
Did you see it? Maybe one more time I
The
show.
steel is quickly oxidized.
There. Goodness. I'm sorry. Okay.
The steel is quickly oxidizing.
There. So you can this is like a layer of oxidization that deposits in the material, but you can see how the grains are flowing inside this because of the pressing, right? You can see that there's like a direction to the whole grains flowing. So it's going like this, this part is going like this, and there's like a small cavity which is forming. Okay,
With all this air exposure,
see.
use a high-pressure water gun to remove the scales of rust. An
Oh,
ingot
yeah. Goodness, I'm sorry again. Don't. Yeah. So you see here. So you see the orientation in which the grains get arranged in such a part. When you're forging, this is how things will look like. The microstructure inside will look like.
An ingot often passes through a die several times or through a series of dies arranged in sequence. Each pressing forms the metal bit by bit into the final shape. Metal is composed of microscopic crystals. Squeezing it in a press bends these crystals, destabilizing the metal structure. But reheating the metal creates new crystals to replace the deformed ones. This restabilizes the structure, and because the new crystals are smaller, makes the metal stronger than before.
Yeah.
That's why finished
Basically, what I said in the past 1 hour in one statement. Oh my God, I'm sorry.
an annealing furnace requires
So let's.
makes the metal stronger than before. That's why finished forgings require heat treatment.
What is happening? Okay, I'm sorry for the technical glitches and all that. Sorry.
Makes the metal stronger than before. That's why finished forgings require heat treatment in what's called an annealing furnace. They heat for a day or two depending on the grade of steel. Then they soak in a water and chemical bath for about 5 hours.
So this is the quenching
Strengthens
process.
the steel even more.
Okay, it hardens the outer layer of the material. Okay,
Finally, workers mount the steel
so
forgings
just
on
look
lathes
at the
and
size of that lathe.
they remove the rust scales that form during heat treatment. Then precision machine the forgings into what the client ordered. Usually industrial parts such as rotors, spindles, and shafts. Many factories prefer to buy forgings in the shape of blocks or bars and machine the parts themselves.
So yeah, so that's how forging to get to a block shape is done, right? But let's take a look at how forging is done
A combination wrench
of a product. Okay, so this is the product. Wrenches are typically made with forging, and
tightens and
let's take a look
loosens
at that.
bolts using its U-shaped open end or its enclosed box.
So there are some other processes also, machining processes also, that you will see here. One is called broaching, that notice it carefully and keep an eye out for it.
And with
Okay.
a hexagonal shape. To start, a steel bar travels into a die cutting machine that cuts it into lengths called billets.
Yeah, so these are billets. So billets is a starting point for the forging. Goodness, I think what is happening is this one gets vanished.
A combination wrench
I'll-
to start that cuts it into lengths called billets.
Okay,
Each billet will become a wrench. One by one, a machine feeds the billets into an induction heater. It heats them to more than 1800 degrees Fahrenheit.
so typically induction heaters are used nowadays because other kind of heating methods are fairly inefficient, but electrical heating is still the most efficient process in which we can do it.
Then sends them into a forging press.
Yeah, so this is where the forging operation starts.
The wrench's general shape.
So the first step, a general shape, but you can see that the dies are kind of kept side by side, and the work is actually done by a single person. He holds the billet, the first operation happens, and it's taken to the second step,
Gives it its finished shape.
and the third one kind of removes the,
Cuts off the excess metal.
yeah, okay. So this again, this part is recycled, and this is what you get out.
The wrenches exit the forge press and cool off on their way into a collection box.
So here you can see it's not yet finished, right? So you can still see the lines where the two dies met. Okay, so even after cutting, you'll still have some amount of flashes, and the hole is not yet made, and the it's a fairly crude process. So since the metal is taken to a red hot temperature and kind of cooled down, there are some scaling which happens, right? And these are like rust scaling which forms. Okay, so those things need to be finished off in further operations.
Then a worker
Okay.
grinds off the trim line, a thin line of excess metal created when the top and bottom dies come together.
So
This bend machine
here they are calling it trim line, but same, flash parting line. All of these are valid terminologies.
gives the box end a 15-degree angle. A vertical milling machine then drills a hole into the box end.
So in the box end, so first step is to remove that material which is not needed, and then the actual shape of giving it that star form.
Using coolant to keep the drill from overheating.
Okay,
This is a hydraulic hex broach machine.
so it's called a hex broach machine. Okay, broaching is this operation, and just take a look at this.
The broach tool is what gives the hole a hexagonal shape.
Okay, yeah. So this is the broaching operation. So you get a near net part, and then you cut off these small portions to get whatever desired shape that you want. Okay.
opened end wrenches also go through a broaching operation. In this case, the broach tool shapes the open end into the desired size.
Right. So here, as you can see, this is the broach tool. It just moves up and down, and these are the cutting. So the cutting blades are arranged sequentially one after the other in slightly incremental, dimensions of removing material.
The wrenches now undergo a three-stage
So it's almost done.
procedure to harden and strengthen the metal.
But the main process is that because of the forging operation, what has happened is that it has kind of imparted the necessary smaller grains that are needed in the whole piece. But there are some internal stresses which are there still. So to remove this, you have to take it through the heat treatment process, which rearranges the crystals. They are smaller than before, but they are still rearranged, and internal stresses in the grains are removed. Okay.
Ceramic stones and a chemical solution polish the wrenches for
This is how it's polished actually in the industry. So these are chemical stone polishing stones, and you have this tumbler which moves on. Sometimes it's a drum also is used, and you would put whatever material is needed in that, and this will rotate and it will polish over time.
8 hours, giving them a bright luster finish.
Okay.
A machine then dips the wrenches into a nickel plating solution that helps make them corrosion resistant.
So
A series of baths then plate the wrenches with trivalent chrome, which is a safer, more environmentally friendly alternative to traditional plating methods.
So chrome plating, this is how it's done.
After a final rinse in water, the wrenches come out with a bright cosmetic finish. Combination wrenches are available in a variety of sets, all conveniently organized and neatly stored.
Yeah, so that's how wrenches are done. And I don't know what this is, but let me just see.
Spending up to 30 hours in a furnace to soften it enough to be worked to remove any rough.
Anyway, I think this video is there, so you go ahead and watch it. It's the same kind of things like forging. It will give you a better understanding of the process, and this is an example of how tuning forks are made. So I just found it interesting and I put it over here. Tuning forks are also forged because they can't be directly machined, because you need certain acoustic qualities in tuning forks. So they need to be forged because you want to arrange the grain structures in a certain manner. Okay. And ball bearings can be formed and made. So you could, if you design the rollers in a certain manner that it pinches the material as it rotates, and you can make ball bearings. You can also directly make ball bearings by a process something like this, but yeah, this is also a process, a high production volume process, right? Okay. And yeah, so let's take a look at some of the design considerations for forging. Okay, so this is, let's say you want to make a forged part, right? So there are few things that you need to consider. Like first and foremost, let's say you want a part which is like this T shape. You can't directly forge a T shape because forging requires a much higher draft angle than casting. Okay, 3 to 5, 7 degrees, it's best to go around 10 degrees. Okay, it's that high. So, okay, 7 to 10 degrees I would say is something like very easily workable. Okay, so first and foremost, what you do is you give let's say you want this finished part, let's say you give some amount of scope for things to be machined off from this surface. Then you give some draft angle like this. Okay, and you give some more additional dimensions for shrinkage, for allowing shrinkage, and then you add these large fillets so that forging can happen. So this, for this T part, the forged part which comes out, it will be of this shape. Okay, and this is how so what happens is that, let's say if you have a very large piece, when you press, you need some space for the material to flow out. Okay, and this is like a relief space, and this uh, technically it's called a gutter. So when you push on the material, some of it flows out this way without damaging the actual design, right? Okay. uh, what are some of the problems that happens in forging? You have things like you know, so you want to forge from this is the starting shape, right? And you press, because of these thin sections, no, you may have kind of ribbing and web formation over here, or the material gets squished together and this kind of lapping of the material happens. So this is a defect. So web defect, lap defects. And sometimes what happens is that if the design is not proper, if the design of the dies are not proper, then the material will kind of flow into each other without fusing the boundaries that have touched, right? So in this case, these two dies are pressed together. The central portion, material from the central portion flows onto these larger, sides, these bigger parts, and the place, there's like a wrinkle which is created here, right? So you can imagine, if you visualize how the material will flow, you can imagine something like this happens. So, and then naturally there are chances that cracks will start propagating from these locations. Okay. Okay, so we have done forging, and what we will do is, let me just review let me just review my slides, how many I have, and based on that I can tell you if we can go on. Right, okay, so let's go on a little bit. So you know what this is? I don't know if you are here. So this one is the Apple iPod Nano, and I want you to say how probably this outer casing was made. Okay, and I mean, I'll not wait for the answer, I'll give you the answer. And the process most likely is something called extrusion. Okay, so let's take a look at extrusion. And
the extrusion process begins with aluminum.
so extrusion is a very common process. Now if you look at these aluminum windows frames that are created, everything is made out of extrusion. If you have seen a CNC machine, a DIY CNC machine, then the frame of that most likely are made with extrusions. These are very versatile. This is quite a versatile process, and it's very interesting to see how it's done.
Billet. These logs are 22 feet long and weigh on average 1,200 pounds. Logs are available in 7-inch, 8-inch, and 10-inch diameter.
Okay.
With alloys such as 6063, 60005.
So these are different alloy blocks. Aluminum blocks. Okay. So yeah, and this is like the starting point.
6463 and 6061. The log or billet is fed into an oven, which heats the aluminum up to around 900 degrees Fahrenheit.
So
this brings the billet
aluminum
to a plastic state, where it is malleable under extreme pressures, but not molten. The log exits the oven and is sheared to an extrudable length, usually about 30 inches, depending on the shape being extruded. The hot 30-inch billet is fed to the extrusion presses by the extrusion loader.
So this thing is going to be loaded onto a press, and this is exactly what I was telling you. The process of making bhujia is similar to this. Okay?
Ram then pushes the billet into the container and applies as much as 3,000 tons of pressure, which squeezes the aluminum
lots
through
of
the
pressures you can
extrusion
add.
die.
And
When
then
the hot
on the other
aluminum is
end,
forced through the extrusion die, the aluminum
This thing is what comes out. The material is pressed from the other side, and this is probably the shape of the cavity that is there over here, and this kind of extrusion comes out.
Takes the shape of the profile in the steel die and exits as a long stock length aluminum extrusion.
So
the entire process is monitored with a digital readout, and all data is stored on servers, which are used to develop extrusion recipes for each specific profile. As the hot aluminum extrusions exit the press, an extrusion puller grips the end of the extrusions. And
so this is done to ensure that there is no warpage when the whole thing extrudes out of the extruder.
Guides the parts along the runout table. This keeps the 900-degree extrusions from twisting and touching each other. On the runout table, a series of fans will cool the parts to room temperature.
So these are fans which instead, let's say in steel it was quenched. In aluminium's case, you don't need to quench it. I mean, here they are not quenching it. Rather, they are using fans to cool down the extrusions. Okay, and you can see these are all the extrusions that have been created. Okay.
At this point in the process, the aluminum extrusions are at a soft state, T4 temper. Post-artificial.
So T4, T3, T6, these are terminologies that denote how what kind of heat treatment processes had been done to the aluminium. Okay, what kind of tempering processes they have gone
Aging
through.
is used to reach harder tempers, such as T5 or T6 tempers. There are other forms of cooling during the extrusion process, such as water quenching, which allow for harder strength tempers through artificial post-aging. Once the aluminum is extruded to the 150-foot table stock length, each piece must be separated from the continuous extrusion process by cutting with special movable hot saws. After separation, the extrusions are transferred to the cooling table, where it is allowed to cool. As the aluminum extrusions cool, they shrink and distort.
So as naturally,
After the parts
okay,
reach room
I think it'll show.
the next process stretches the aluminum back to its non-distorted condition.
Shit.
And stretching the next process stretches the aluminum back to its non-distorted condition.
So once the aluminum kind of cools down, naturally it will shrink, right? So, and you cannot very clearly say how it will shrink, okay, or very easily say. There might be some warpages, some dimensional changes which may happen at a so as you can see, these are very, very long pieces, right? So some dimensional inaccuracies in the middle may happen. So this kind of a process is used to ensure you have a more or less uniform and straight extrusion.
The stretching operation is achieved by gripping the extrusion on both ends and stretching the aluminum approximately 3% of its.
So this part actually shows you the strength of that. So this gripper is exerting so much amount of force, and the other thing is the cross section that you see is solar. So you can have a very high thickness, wall thickness part also be made from extrusion.
Total length. This straightens and brings all dimensions and tolerances into spec. Then the parts travel to the finish saw, which will cut the long table length extrusions into predetermined stock lengths, 20 feet or less.
Okay, here you can see this particular extrusion shape. It has a hole in the center. It is possible to get a hole in the center. Okay.
Extrusions are then loaded onto aging carts and are fed into an artificial age oven, which gives the parts a T5 or T6 temper hardness. An extrusion.
So the process of heat treatment of aluminium is slightly different, or I think much different than that of aluminium. You use a different kind of temperature variation to get it to the right tempering, right kind of hardness and mechanical properties.
Die is made of H13 steel and comes in various sizes.
So this is what the die looks like. What is the extrusion die looks like? Okay, from one of the ends, I think it is from the other end that the material is pushed in, and from this end it comes out. So wherever you have like a hole, what happens is that there are subsequent stages inside the die. There are subsequent stages. First, let's say you want to make a square cross section kind of an extrusion, closed hollow in the center. So you would first extrude this kind of a shape, and subsequently after that die there'll be another die which kind of presses these two ends together, and since the metal is hot, it fuses at that point. Okay, and that's how you get these kind of closed cross section or closed kind of extrusion.
And with a varying number of profile holes.
See?
Some dies are as large as 15 inches in diameter and can have between 1.
So as you can see, the die shape is quite simple, right? So you can actually manufacture this quite easily. It's not as complicated as let's say injection molding die. So extrusion has this benefit. The die itself is quite cheap than other processes. So that's why extrusion, I mean, if the industry is there, if the machines are already set up, then the initial investment cost in getting extrusions done is much lesser than, let's say, going for injection molding or something like that, because there you have to make, in injection molding you have to make a much costlier dies. Okay,
and 8 profile holes, depending on desired extrusion design pressures. Today, Custom Aluminum Products has produced 12,000 custom designed profiles.
so
Please allow Custom Aluminum Products to assist in the die design process. By working together, we believe we can reach the best possible design at the lowest cost to
naturally
our customers.
it starts off with
To learn more
CAD.
about our
Okay, anyway, so this is the schematic of the whole thing, how it works. You have a container which houses all of the things, and then you have a liner. Probably, most likely this is graphite, because you need something which has very less friction with the billet. Okay, and the billet is the aluminum piece. Okay, and you have a few things which are needed. So first one is like a dummy block, a block which separates the press, the piston, from the block, from the billet. The billet is at a high temperature, so directly having it contact the pressing stem is not a good idea. So you have a dummy block over here, and then you have the actual die, which you saw in the video somebody was cleaning. Okay, and then you have something which presses the die onto the whole thing. Okay, and now this setup is ready, and when you press, this comes out of the other end as an extrusion. Okay, and the best part of extrusion is that for simple objects like this, let's say this is like a clothes rack. Okay, you can imagine if you have a window curtain rod, then you can design some kind of an extrusion which you cut in sections, and you get the final product ready. Okay, you have this is the extrusion that was done, and it was cut, and 2 holes were drilled, and the product is ready. This is a gear, a simple gear or a ratchet, and you have the extrusion done like this, and you cut it, and some machining operations later you have the ratchet ready. Similarly, something like this part. Okay, and these are some of the classifications and types of extrusion that are there. So you can have a solid extrusion, you have a solid symmetrical shape, you can have slightly asymmetrical, and also hollow. You can have this kind of profile, or this kind of profile with a some gap and a large hole. Okay, and depending on the gap width, there are 2 types of classes that you have. One is where, let's say, the overhang from the walls to the gap, right, is equal on both sides. So this is called class 1. Okay, and this is called class 2, where the overhang is much larger. Okay, so these are different ways of classifying extrusions. And then you can have based on the hollow profiles. Okay, if you have a simple round hollow void, then it's a class 1. If you have like a slightly more complex but the same shape probably as the outer this thing, it's called a class 2. And if you have more intricate details, multiple holes, then it's called a class 3 extrusion. Okay. Right. So as I said, how would you do like a hollow thing? So you would need a chamber. So let's say this is the die. This is like the okay. So I think from here the material is passed. Okay, and you have this kind of a place where, or and this is the die, right? So you have this kind of place where the material kind of differentiates or divides itself into 2 or 3 parts, goes through some other parts, and joins at the end. I could not find a video of this. If you find it, please do share. Okay. And some people have done some like really amazing work with extrusion. So this one is an extruded chair, and the uniqueness of this product comes from the fact that you have not the better part of the extrusion, but the ones which is slightly deformed. So it has this unique look and feel to it. So every part is different, right? And so this, let me move myself to the other side so you can see, right? So you have this kind of a shape where the extrusion, the initial part of the extrusion is what is actually the product, okay? And then this is a nice, very nice chair that was, it's like a airport seating bench, okay? And all these parts that you see are extruded. In fact, these are also extruded and cut into the necessary dimensions. Some of the machining operations done over here and all that. Okay, it's really nice design and all that. Okay, let's go forward. So how should you design for extrusions? First and foremost, it's always a good idea to have uniform wall thicknesses. Okay, this reduces the stresses on the die. This reduces the complications of the die design. Okay, so all these places, so you have uniform wall thicknesses. And where you can't really have uniform wall thicknesses, what you can do is you can have ribs instead of that such a feature. Okay. Yeah, something like that, Aditya. Anyway, then the other thing is always try to have some fillets in the whole thing. Fillets are essential in almost all of the manufacturing process, except for, let's say, machining. Okay, so fillets are important, so you put some fillets. And sometimes when you have a very uniform kind of a round shape, it may not be very easily achievable in extrusion. Rather, you can have like this kind of a relief holes which enables such things to happen. Okay, similarly, very sharp angles are you should not have, and very sharp corners with acute angles, try to avoid. So these are like generic design considerations. Yeah, and sometimes what happens is, see, making this is much easier than making this. So this one is like a class 1 type of a hole where both lips are of equal distance, but this is large cavity and it needs a die. It can be done easily, but rather, why not make something like this, and when you are making the product, just bend it a little bit and get the final desired shape. So this one is cheaper to manufacture in extrusion than this. Okay, similarly, let's say this, instead of this kind of a design with square and straight edges, let's say if you want to fit a block, a flat piece of flat metal somewhere inside like this, in this such a feature, so better design something like this, right? So this one, it looks it's much easier to extrude. This is also possible to be extruded, but look at the number of holes and the cavities that are there. This may need 2 or 3 different welding welding dies. Rather, if you can change the design in the manner that it is extruded in 2 forms and both of them join together to form the final one necessary, this is a better idea. Okay, and wherever possible, try to avoid having holes unless it is absolutely necessary. Okay. uh, so you can design extrusions which kind of join together, so which can nest together. The same extrusion, if you orient it differently, join it, it can be designed that way. So this one gives you an example. So one is this extrusion, one is that extrusion, right? So one is this extrusion, this itself, if it's rotated the other way, you can probably join it like this, and you can hide the joineries quite interestingly if you design the right, shape, form of this. And yeah, so this one is a product which uses extruded parts. So this and this and this are three different extrusions, and this is a photograph that shows you all the different extrusions that may be available to you in the market. Okay. I want to see, yeah, I think my photograph was, yeah, I think this one is more visible now, right? So this one is what I was explaining. Okay, so have it this way, not this way. Okay, right, and then, so what we will do is we will stop here. We have been going for an hour and 50 minutes, I think. So we'll stop here, and we still have a few topics to discuss in this, especially some specific type of extrusion processes. Okay, impact extrusion is one which is very interesting, and bending we hadn't discussed, but you already explored bending in fusion, but we'll discuss how things need to be bent. Okay, and we have this process of drawing and deep drawing, we'll discuss that, and spinning. So this, it won't take much time, but I think we shouldn't go on for so long. So we'll stop here, and these few topics, I think there are not many slides, like 2 or 3 slides, right? So and there are some interesting videos to watch. We'll take a look at all of this later on in the next class. Okay, yeah, so that's about it for today's class. Let's see how many people are alive in the chat. If you are there, just say hi, and or say whatever, and we'll close the class today. It's nearly evening over here, and yeah, I hope you learnt a little bit. Yeah, hi Vedant. Okay. So I hope you learnt a little bit about forming, and these few topics we'll discuss in the next class. And right, so your assignments are already given to you, 5th and 6th assignment. Tomorrow's class will not be there. Please utilize tomorrow's time for doing your pending assignments. All of the people who have not done assignments, if they are getting time, please utilize it for that. Yeah, hi everyone, good to see that everyone is alive. Okay, nice to have you. Okay, so we'll close here. Tomorrow no class. Tomorrow please do the assignments and submit it, whoever has not done. Okay, is my background from Red Dead Redemption? Yes, it is. Madhav, yes. Red Dead Redemption 2. Okay. Can I send you a screenshot in mail or for approval? What, I don't know what you are meaning by that, Aditya. Okay, let's do like a small question answer session. If you have any questions, please type in. I'll wait till this message reaches you and your messages reaches me. Okay. Yeah, I'm a big fan of Red Dead Redemption. 2. I haven't played 1, but yeah, 2. My goodness, what an amazing game. Aditya, for the assignment. Can I send you a screenshot for mail for approval? What, Aditya, you don't need approval. Just submit, man. Why do you need approvals? It's an assignment. It's not a project. Submit directly, Aditya. Okay. Okay. Demon Gaming. I forget who Demon Gaming was. Yeah, just give me again. PC Master Race, man. All forever. Come on, is that a question? Okay. So if you don't have any questions related to the class, then we'll call it a day. And yeah, maybe when we meet, I can answer all of these questions from Amir. What are the games that I play? Amir, you have to do your assignments, man. I don't know what you are doing. Okay. Okay. Right. Okay. Thank you so much for being in the class, and please review whatever material, whatever is there in the OneNotes and all that. And yeah, have fun. I mean, don't have fun. Work hard tomorrow. Okay. I'll see you. I'll see you. Yeah. Have fun. I mean, don't have fun. Work hard. Yeah. See you guys. Bye bye.